Hello. Um, in the following tutorial, I'm going to cover the example we had in the module number 9 slides. And this is going to be the same question we have in the assignment number 4. And I will give you the tutorial in two parts. The first one, we're going to cover the question in the lecture slides. Actually, you have a recording for the lecture itself available on the Canvas, and later again to do the solution step by step on paper using the question we have in the assignment itself. So let's go through the slide here. The main thing is one of the planning process we have for the manufacturing process is we try to usually get the optimized uh, speed of the cutting we have in the machine operation that will result in the best tool life. Now, why are we doing that? Because simply we don't want to stop the manufacturing process each time to change the cutting tool. This will be a waste of time during the manufacturing process, and this will lead to the reduction in the production rate in the manufacturing processes. So to determine the cutting conditions and the manufacturing times, the machine conditions mainly going to be the cutting speed, the feed rate, and the depth of the cut. If I'm going to increase the cutting speed and the feed rate and depth of the cut, I'm going to reduce the time required for machining the part. But at the same time, this will lead on more, uh, it can cause the erosion of the cutting tool, and thus we get to reduce the tool life. So usually the object is to set the cutting condition in such way that the economically best production state is going to be achieved. So what do you mean by the best economically production state? Is going to be the one which is going to have the minimum production cost, but the maximum production rate. Usually these things are going to be available all the time. So we need to have a wide range of the test, trial and error processes until again to achieve the optimum tool life, which can be achieved as the optimum cutting speed. So in general, the choice of the feed we either get to have the finishing cut or the roughing cut. In the finishing cut, we just need to get the best surface finishing. So this usually going to have a relatively lower feed rate. We don't want to remove the material at higher rate, we just want to get a good surface finishing. The other choice is going to be for the roughing cut. In that case, the feed rate is not going to be effective as a cutting speed overall tool life. Therefore, the feed rate should be set to have a maximum possible value because we want to remove the material at the maximum rate of the material removal, which is actually the main parameter of that is going to be the depth of the cut and the feed rate. The limitation we have is that the maximum tool force, that's the machine or the tool, can stand, and the maximum power available are going to be the main limitation for the process. The choice of the cutting speed, we can either use the high speed or the low speed. Usually the high speed will reduce the tool life. Because we have something we're going to see it on next slide. It's called the Taylor equation. In the Taylor equation, we have a relationship between the speed of the cutting or the velocity of the cutting and the tool life. Usually this will be look like a line with a slope, and this slope value is equal to n. And whenever we're going to have that the speed of the cutting multiplied by the tool life up to power n parameter is going to be equal to a constant. This will tell me that whenever I'm going to increase the speed of the velocity of the cutting, I'll reduce the tool life and vice versa. So once again, at high velocity, we're going to have low tool life, highest tool cost, and high production rate, but shorter production time. Now, high production rate because the cutting time is going to be reduced, but shorter production rate because we need to stop from time to time to change the tool itself. At low speed, we're going to have higher tool life, but low tool cost, which both are going to be advantage. On the other side, the disadvantage is going to be low production rate because the time of the cutting is going to be longer and long production time. So these 2 points are going to be linked together. The cost per components usually is going to be equal to the non-productive cost plus the machining cost plus the tool changing cost plus the tooling cost itself. If I am to describe this equation as a numbers, it's going to be written as the following. The cost of the unit is equal to the cost of labor multiplied by the overhead time, which is the non-productive time, plus the cost of labor multiplied by the cost of the time of the machining per piece. Plus, we're going to have the tool changing cost, which is going to be equal to the labor cost multiplied by the tool changing time. And this we're going to be multiplied by the ratio of the tool, uh, the machining time divided by the total tool life. Finally, we're going to add the tooling cost, which is going to be equal to the cost of the tool multiplied by the ratio of the time changing of the tool divided by the tool, the machining time divided by the tool life. We can find two values for that, the minimum and the maximum, and this will depend mainly on the speed we are going to use for this operation. For a single pass turning operation, the time of the machining will depend on both the diameter and the length of the cut. And of course, we are going to have the cutting speed and the feed rate. You know that in turning operation, the feed rate is going to be in millimeter per revolution. This is not the linear feed rate, this is rotational feed rate. While the cutting speed is going to be the speed of the point which is going to be turning on the part itself and on its circumference, but is going to be calculated as a linear velocity. So the time of the machining in general is going to be equal to the pi multiplied by the length of the cut multiplied by the diameter of the part and divided by the cutting speed multiplied by the the rotational feed rate. On the other side, the Taylor equation of tool life is going to be equal to the cutting speed multiplied by the tool life up to power Taylor exponent n is going to be equal to a constant, which is the cutting speed for 1 minute of the tool life. So if I get to combine the above equation in one, I can get the following equation for the cost price per piece. So once again, this is non-productive time. This will be the machining time, the tool changing time, and the cost of the tool. This equation is going to be used to calculate the cost per unit by using both the time required for by using the minimum speed or velocity and the time required by using the maximum velocity. So to do that, we are going to have the two sets of the equation. This will be the differentiating of this equation with respect of the cutting speed and equating to zero, then solving for the cutting speed, and this will give me the cutting speed for the minimum production cost is going to be as following. The V minimum is going to be equal to the C constant we have from the Taylor equation divided by 1 over n, which is the Taylor exponent minus 1, multiplied by the COTD plus the CT divided by the CO, all up to power n. The T minimum, which is it's not the minimum time, actually this will be longer than the T maximum because this we call minimum because it's related to the minimum velocity of the cutting. This T minimum can be calculated with this equation. For the V maximum, the equation is going to be more simpler because we are not going to use the parameters of the cost of the operation and the cost of the cost of the tool and the tool changing time, but instead of that, it's going to be this simple equation. The T maximum, which is going to be shorter than the T minimum because the higher velocity is going to be used, is going to be given by the following equation. Now, the maximum production rate, the time per piece is going to be equal to the non-productive time plus the machining time plus the tool changing time. And if I get to write down that by using the parameters we defined earlier, it's going to be written as following. TL plus the TC plus the TD multiplied by the ratio of the TC over the total tool life. Or we can replace the value for the TC and this equation, and we're going to get this following equation. The lead time that's required to use all the parts together is going to be given by the equation that's the S, which is the measure set of time. If we have NE plus the TU, which is the production time per one piece, multiplied by the lot size. Now, in the following equation, we have a lot of 500 units. So the Q here is 500. And we have the steel rod, which have the length of 30 centimeters, and the diameter is 6 centimeters. It's going to be turned on the CNC machine. Let me get it done here. It's going to be used on turned on the CNC lathe machine at the feed rate of 0.2 millimeter per revolution. The depth of cut is 1 millimeter. The tool life is given by the Taylor equation as following. So the C is 200 and the N is equal to 0.2. The other data given for this question are the machine labor rate is $10 per hour. The machine overhead rate is going to be 50% of the labor cost, which is $5. The grinding labor rate is $10 per hour, and the grinding overhead rate is 50% of the grinding labor. The work piece loading and unloading time is going to be 0.5 minutes per piece. The tool is going to be brazed insert. The cost of the tool is $27.96 per tool. The grinding time per edge is going to be 2 minutes. The tool changing time is going to take 0.5 minutes per edge. The tool can be ground only 5 times before it's going to be discarded. So we have 5 edges can be grinded before we're going to discard the tool. Just remember that the tool itself is going to have a fresh tool edge that we can use at the beginning. Now, what we need from this question is to find the optimum tool life and the optimum cutting speed to minimize the cost. Second, the optimum tool life and the optimum cutting speed to maximize the production rate. And we know you can see that actually the cost is going to be lower at the minimum speed because the tool life is going to be saved. But the problem is that the production rate is going to be longer. To maximum the production rate, we need to have the optimum tool life at the maximum speed. So to do that, actually, we need to have something like, for example, an Excel sheet, and we can have multiple calculations until we can have the optimal value for the V that can produce the increase the tool life, and thus is going to optimize the value for the production rate and the minimum cost. Also, we need to find the minimum cost per component, the TU, and the type of components and the corresponding lead time. Also, the maximum production rate, the corresponding cost per components, and the lead time. Now, just remember something. These are different from the things required to be done in the question again to have in the assignment. I'm going to explain that very soon. So the solution is going to be start first with finding the value for the CO and the value for the CT. The CO is the time we're going to spend on the cost of the labor per minute, how many dollars per minute, while the CT is going to be the cost of the edge of the cutting tool. So the CO is going to be equal to labor cost, which is $10, plus the overhead cost, which is 50%. 50% of the labor cost. So that's why you can see that we have 0.5, which is $5. This is your overhead cost. Okay, and I don't know how to write overhead cost, and this is the labor cost. And divided by 60, because this is dollar per hour. We want to change it to dollar per minute, so I have to have it as $0.25 per minute is the labor cost, plus the overhead cost. And now for the cost of the tool, we have 27.96 is the cost of the tool itself, divided by 6. Why 6? Because we have one edge with the tool, one fresh edge, plus 5 possible grinding. So this will be 6. Now, in this part, we are going to have the grinding of the tool cost. We have 2 minutes to be spent on the grinding. the cost is going to be $10 plus 50% of the $10, and this will make it $15. That's per hour divided by 60, and is going to be in total $5.16 per age. Now we found the CO and the CT, and then we're going to apply it to the equations to find the value first for the T minimum, and then we're going to find the V minimum, which is related to it, and then later we're going to go for the T maximum and the V maximum. So start with the T minimum. The N was given as 0.2. The CO is here. The TD is given as 0.5, which is the tool changing time. And the tool of the course is this value. Okay, so we just substitute these values and we're going to get that the T minimum or the minimum at the minimum speed, the tool life is going to be 84.56 minutes. Now, the velocity of the cutting required to achieve this tool life is going to be found by Taylor equation rearrangement, which is going to be equal to 200, which is the C, divided by the 84.56 up to power n, which is 0.2. And that's means we need to run the machining at 82.3 meter per minute speed velocity of the cutting to achieve the tool life of 84.56. Now, for the maximum tool life, which is related to the maximum speed we're going to have. So the T maximum is going to be 1 over n minus 1 multiplied by the TD. So 1 over 0.2 minus 1, and then we're going to multiply by the tool changing time, which is 0.5 minutes, and this will give me 2 minutes. So that will be done if I'm going to run the cutting tool at the speed of the cutting of 174.1 meter per minute. So you can see this is the actual V maximum, this is the V minimum. When we say T minimum, because it's related to the minimum speed. When we say T maximum, because it's related to the maximum speed. So this will actually, it's going to run only for 2 minutes before we need to change the tool. And that's why the production rate can be considered to be the highest, but the tool cost is going to be too much because we need to change the tool every 2 minutes. We need to stop, we change the tool, and return back to the operation. So both values are actually not reasonable. And as I told you once again, we'll just calculate the maximum and the minimum. But in the real life scenario, we need to calculate as much as we can and find the optimum value. Now, for the minimum cost, which is related to the minimum velocity, okay, we are going to calculate as the pi multiplied by the length of the cutting multiplied by the diameter divided by the velocity minimum multiplied by the rotational feed rate. So we have 3.14 revolution. That's the 2 pi, the pi, and we have the 300, which is 30 centimeters, and we have the 60, which is the 6 centimeters diameter. The B is 82.3 meter per minute, and we have the feed rate is 0.2 millimeter per revolution. So, of course, the revolution will go with the radius. We have the 1000 because we have here millimeters and millimeters. We need to change the meters here to millimeters, so multiply by 1000. And then we are going to find that the minimum cost should be done first by picking what will be the time required for the machining for one piece at the minimum velocity, and this will be equal to 3.4 minute per piece. So now we're going to calculate the cost, and this will be equal to the CO that we calculated earlier, multiplied by the value for the tool changing time. Sorry, not tool changing time. This is the loading and unloading time. Plus the cost of the machining, the time of the machining here, multiplied by the cost of labor, and plus the tool changing time here, plus the tool cost per edge. So this here is going to be substituting all the figures we had earlier, and we will find that the cost of the piece is going to be equal to $1.2 per piece if we're going to run the machining at the minimum velocity. Now we go to the time per component, and this will be equal to the loading unloading time plus the time of the machining plus the tool changing time. So we can add these value by using this equation, substitute that, and we're going to get that the time is going to be equal to 3.95 minutes per piece are required. Now we would like to know what will be the total time. We have 500 units, and each unit is going to take 3.95 minutes, and thus we are going to have that the total time required to make the whole patch is going to be equal to 1976.4 minutes. Now we're going to repeat the same process by using the maximum velocity. I mean, we're going to find the maximum production rate first. So we start with um, that's the TC, calculate the TC value. Okay, so TC value by using the V maximum, of course, is going to be shorter because the speed of the cutting is faster. So it's going to be 1.62 minutes. The TU in that case is going to be replacing the first TCU by this one, and we're going to end up by the time is going to be dropped down to 2.53 minutes per piece. And thus the lead time itself is going to be reduced to be 1,264.4 minutes. Now the cost of the maximum, for maximum production rate, once again, we're going to use the CU equation. Just remember that the TC value has been reduced, and I expect that the cost actually is going to be calculated once again, and we will find that the CU value is going to be equal to $4.82 per piece. Okay, now these are the equations, and we will see what we are going to have in our assignment. Just give me 1 second. Let me get out of here. Discard it. So the assignment question. Now this one actually is available for you on the canvas. So what we can see here, and we're going to come back to this one to solve it later. Now we have the process of planning, the tool life, and the production rate. The steel rod of 400 plus R millimeter for the length, and the diameter of 54 plus B millimeters are to be turned on numerical control lathe machine in a loss of 1,350 plus a Q. Now let's see what are the Q. If your student number is going to be equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, the P is going to be the first digit. The R is going to be the two last digits, and the Q is going to be the three last digits. I know I should go PQR, but it's happened like that. So the data we have for this equation is the feed rate, the depth of the cut, the tool life formula for the high-speed steel cutting tool, the machine labor cost, the overhead rate for the labor, the grinding labor rate, and the loading and unloading time. Now, of course, here we didn't mention that the grinding labor rate for the overhead is going to be the same thing, 60 plus P%. Once again, we said that we're using the high-speed steel cutting tool, which had the tool cost of 45 plus P with a tool changing time of 3 minutes. So we need to find the tool can be ground for 7 times before it's going to be discarded. The grinding time is going to be 3.5 plus R divided by 20 minutes. Bear in mind the following, assuming a single path. First, the optimum tool life and the optimum cutting speed to minimize the cost per piece. Second, the production rate for the minimum cost creations. Second, the optimum tool life and the optimum cutting speed to maximum the production rate. And finally, the production rate of the maximum production rate creations. Later, we need to redo the calculation if a throwaway carbide insert is going to be used with a cutting four edges, which have the total cost of 40 plus Q divided by $100, and the tool changing time of 3 minutes. And the tool life formula is going to be changed to the following. So Later, you need to write down a brief comparison between the two cases, the high-speed steel tool and the disposable insert. We're going to do the solution in the next video.